Hello everyone and welcome back. Today we're going to explore a fascinating concept in mathematics, one that might just blow your mind. You've probably heard of Euler's identity, which many consider one of the most beautiful equations in math. It connects 5 essential constants, and it looks like this. E raised to the power of pi times I equals -1. Now, while that equation is beautiful, today I'm going to show you something even more incredible. It involves just 3 or 4 numbers, and it starts like this. J raised to the power of 0 equals plus or minus 1. I know, it sounds a bit strange, but stay with me. This is no joke. This is a real mathematical truth, and I'm going to prove it to you step by step. You might already know that any number raised to the power of 0 equals 1. But what if I told you that j raised to the power of 0 can also equal -1? It's true, and I'll explain exactly why. First, let's look at the equation j raised to the power of 0 equals -1. You might think this can't possibly be true for regular numbers, complex numbers or real numbers, because they don't satisfy this equation. But guess what? There's a special system of numbers that can solve it, and that's where virtual numbers come in. For those of you who may not be familiar with the virtual number system, let me give you a quick explanation. In my system, I define j as the virtual unit, and it's actually the logarithm of -1. So j is defined as the logarithm of -1. Let's move forward with this idea and see why j raised to the power of 0 equals -1. Here's how we can prove it. First, let's substitute j for x in the equation. So now we have j raised to the power of 0 equals -1 numbers. Let's replace 0 with this difference, like this. J raised to the power of 1 minus 1 equals -1. Now, using the rules of exponents, we know we can split this equation into 2 parts. So we can rewrite it like this. J raised to the power of 1 times j raised to the power of -1 equals -1. Next, we can move the term j raised to the power of -1 to the denominator, so we get j divided by j equals -1. Now let's use a bit of algebra to solve this. If we move j from the denominator to the other side, we get j equals -j. Next, let's move the -j over to the left-hand side, so we have j plus j equals 0. Now, remember that j is defined as the logarithm of -1. So we can rewrite this equation like this. Logarithm of -1 plus the logarithm of -1 equals 0. Using a property of logarithms, we know that we can combine these 2 logarithms. So we get logarithm of -1 times -1 equals 0. This simplifies down to logarithm of 1 equals 0. And now we've reached a point where both sides of the equation are equal. 0 equals 0. This proves that j satisfies the equation j raised to the power of 0 equals -1. So why is this true? The key lies in the structure of the virtual number system. Unlike traditional complex numbers, which are two-dimensional, the virtual number system is only partially two-dimensional. This means it doesn't have negative quadrants, which is what makes this equation possible. This also provides a challenge to the Fundamental Theorem of Algebra, which says that equations like x raised to the power of 0 plus 1 equals 0 have no solution. But we've just proven that x equals j is a solution. This opens up an entirely new perspective on how we can think about numbers and systems in mathematics. Virtual numbers offer new possibilities, and I believe they can even outperform the complex number system. Now, some of you might be thinking that j, or the logarithm of -1, is just the same as pi times the square root of -1, which we usually define as I. And you might argue that it's not possible for j to equal -j. After all, in the complex number system, we know that pi times I equals -pi times I, which leads us to a strange conclusion where 2 times pi times I equals 0 or 2 pi equals 0. This might seem nonsensical, but here's the thing. These kinds of statements still make sense within the complex number system because complex numbers are not about precise measurements. They represent rotations. For example, the square root of -1 corresponds to a 90-degree rotation. So, in this rotational system, both 0 and 2 pi are the same because they represent the same point after a full rotation. Let's test this idea with some basic trigonometry. If we take the cosine of 2 pi, we get the same result as the cosine of 0, and if we take the sine of 2 pi, we get the same result as the sine of 0. If we multiply both sides of the sine equations by I, we get I times the sine of 2 pi equals I times the sine of 0. Now, if we add these two equations together, we have cosine of 2 pi plus I times the sine of 2 pi equals cosine of 0 plus I times the sine of 0. This simplifies down to e raised to the power of 2 times pi times I equals 1. And as you can see, this leads us back to Euler's famous equation, e raised to the power of pi times I equals negative 1. So what do you think of this new mathematical identity? Do you believe the fundamental theorem of algebra needs to be redefined, or is it still valid? I'd love to hear your thoughts in the comments. Also, what do you think about the virtual number system? Do you think it's better than the complex number system? If you enjoyed this video, don't forget to like, comment, and subscribe to the channel. Your support really helps me create more videos like this. Thanks for watching, and I'll see you in the next one.